Okay, I'm recording now. Let's do an example in which we have to find the unit tangent vector at a point corresponding to a given value of a function. Let's find the unit tangent vector t hat at the point corresponding to the given value of the parameter t where our vector function is given as r vector of t is equal to t sine of t for the x component, t cosine of t for the y component, and t for the z component, evaluated at t equals pi over 2. Well, let's recall what a tangent vector is. A tangent vector is a vector that is tangent to a curve at a point in space. For example, let's say we have a parameterized curve of some vector function, and let's say this is the vector function r of t. And we want it to find the unit tangent vector at this point. Well, at that point, our r vector is the position vector drawn from the origin, and there is a tangent vector, a vector tangent to our curve at that point. That tangent vector would look roughly like this, and I'll label this tangent vector as t vector. Now that tangent vector is just equal to the derivative of our vector function at that point. Just like when we had normal functions that were unparameterized, the slope of the line at a given point represents the derivative of our function at that point. The same is true for vector functions. The tangent vector at a given point of a vector function is equal to the derivative of that vector function at that point. Now, this problem is asking us to find the unit tangent vector at a particular point. So that's going to be a vector that's in the same direction as our tangent vector, but has a magnitude of 1. So you might recall that a unit vector is defined to be a vector divided by its magnitude. In this case, this vector t vector, remember t vector, the tangent vector, is equal to the derivative of our position vector, and then this is going to be divided by the magnitude of the derivative of our position vector. This is what we're going to need to evaluate in order to find the tangent vector of the given function. So let's do this. Let's do this by first finding the derivative of our position vector, which will be a tangent vector. So the tangent vector is equal to the derivative of our position vector, and the derivative of our position vector is found by just taking the derivatives of each of the components of our position vector with respect to t. So the x component will be the derivative of the x component with respect to t, the derivative of the y component with respect to t, and the derivative of the z component with respect to t. For the x component, we can apply the product rule. The product rule says take the first term and multiply it by the derivative of the second term, and then add the derivative of the first term times the second term. This is the x component. The y component is similar. In applying the product rule, we have the first term times the derivative of the second term plus the derivative of the first term times the second term. And for the z component, this is easy. The derivative with respect to t of t is just 1. Well, evaluating the derivative of sine of t ends up being cosine of t. The derivative of t with respect to itself ends up being 1, as I should have indicated here as well. The derivative of cosine of t is equal to minus sine of t, and the derivative of t with respect to itself is 1. This means that the tangent vector has components of t cosine of t plus sine of t and minus t sine of t plus cosine of t and 1. To find the unit tangent vector, it is equal to the tangent vector divided by the magnitude of the tangent vector, which again is just the derivative of the position vector divided by the magnitude of the derivative of the position vector. Well, we have now found the tangent vector. Let's find its magnitude. But to do this, we're going to go ahead and apply the fact that we know that this is evaluated for the value of t is equal to pi over 2. So let's find what the tangent vector is when t is equal to pi over 2. This then becomes pi over 2 cosine of pi over 2 plus sine of pi over 2 for the x component, and then minus pi over 2 sine of pi over 2 plus cosine of pi over 2 for the y component, and then 1 for the z component. Well, we know that the cosine of pi over 2 is 0, so each term with the cosine of pi over 2, we're going to evaluate that to 0. We know the sine of pi over 2 is just 1. This means that the tangent vector evaluated at pi over 2 is equal to 1 for the x component minus pi over 2 for the y component and 1 for the z component. Now that we know what the components of the tangent vector are evaluated at t equals pi over 2, we can now find the magnitude of the tangent vector at pi over 2. We'll need this in order to find the unit tangent vector. The magnitude of the tangent vector evaluated at pi over 2 is equal to the square root of the sum of the squares of the components, x component squared plus the y component squared plus the z component squared. This is the square root of 2 plus pi squared over 4. Now that we have the tangent vector at pi over 2 and the magnitude of the tangent vector at pi over 2, we can now find the unit tangent vector at pi over 2. The unit tangent vector at pi over 2 is equal to the tangent vector at pi over 2 divided by the magnitude of the tangent vector at pi over 2. This is 1 minus pi over 2, 1, divided by 2 plus pi squared over 4, and that's underneath the square root. Because I don't like fractions under radicals, I'm going to just take another couple of steps here to clean this up a little bit. So I'm going to factor out a 1/4 from the expression in the radical. So this will be 8 plus pi squared, and that is the square root. And we have the vector whose components are 1 minus pi over 2 and 1. This means that our unit tangent vector evaluated at pi over 2 is equal to, well, let's look at this. The square root of 1/4 is 1/2. We could flip and multiply, and in the numerator we have 2, in the denominator we have the square root of 8 plus pi squared, and then we have 1 minus pi over 2 and 1. I'll just do one more step, and that's just to distribute the 2 into our components. So we have 1 over the square root of 8 plus pi squared times 2 minus pi and 2. We have now found the unit tangent vector at the point pi over 2 for the function given by r vector is equal to t sine t, t cosine t, and t for the x, y, and z components respectively.